Hello everyone, we are Team Haha. Today, we will compare two deep learning models, LSTM and Transformer Encoder, on a news classification task. Let's get started. Here is what we will cover today. Dataset and model structures first, then the main results and training curves. After that, the evaluation study, discussion, failure analysis, and conclusion. The dataset we use is AG News, a four-class English news classification benchmark. The four categories are world, sports, business, and sci-tech, and all classes are balanced. We split the data into 108,000 for training, 12,000 for validation, and 7,600 for the final test. Both models use the exact same pre-processing pipeline, so the comparison is fair. Here are the two model structure. LSTM stands for long short-term memory. It is a type of recurrent network that reads text word by word. At each step, it uses three internal gates, input, forget, and output, that decide what information to keep and what to discard. Our model stacks two LSTM layers and uses the final hidden state to classify the text with about 3.48 million parameters. Transformer works differently. Instead of reading one word at a time, it looks at all words at once and uses self-attention to figure out which words are related to each other. Since it has no built-in sense of word order, we add positional encoding, which tells the model where each word sits in the sentence. Our model has two encoder layers and about 2.83 million parameters. Here are the test set results. LSTM achieved 92.76% accuracy and 92.75% macro F1. Transformer achieved 91.30% and 91.27%. LSTM was better by about 1.46 percentage points. Macro F1 averages the F1 score for each class equally, which gives a clearer picture of per-class performance than accuracy alone. With balanced classes like AG News, the two numbers end up very similar. Let's just look at the per-class results. Sports was the easiest, with both models scoring over 98%. Business was the hardest, with both models most often confusing it with sci-tech because tech company articles and science articles share a lot of the same vocabulary. Now, let's just look at how the two models actually learned over time. For LSTM, training loss at epoch 1 was 1.387, which is almost exact the natural log of 4, the loss you get when a 4-class model is just guessing randomly. Validation accuracy was 25% at epoch 1, 40.9% at epoch 2, then suddenly jumped into 88.9% at epoch 3. We call this a pace transition, where the model stays near random and then starts working almost all at once. Transformer was very different. It reached 89.2% validation accuracy at epoch 1 with smooth and steady convergence from there. But from epoch 3 onward, training loss kept going down, while validation loss kept going up. This is overfitting, which means the model starts memorizing training data instead of learning to generalize. At epoch 10, the gap between training and validation loss was 0.275 for Transformer compared to only 0.089 for LSTM. Here are the confusion metrics for both models. The biggest shared error is business predicted as sci-tech, 145 times for LSTM and 158 for Transformer. Sport was the cleanest, with both models correctly classifying over 1,871 out of 1,900 samples. Transformer confused world with sci-tech slightly more than LSTM, 66 times versus 54. An ablation study tests how model performance change when something is reduced or removed. Here, we reduced the training data to 25%, 50%, and 100% to see how sensitive each model is to data size. Our hypothesis was that Transformer would struggle more with less data since attention mechanism need more examples to learn from. The result was the opposite. LSTM failed completely at both 25% and 50%. Validation accuracy stays at 25%, basically random, with F1 near 0.10. Transformer held 87.86% at 25%, dropping only about 3.5 points from the full data result. We can explain LSTM's failure using the phase transition. For the transition to happen, the model needs roughly 15,000 to 17,000 total gradient updates. At 25% data over 15 epochs, LSTM only gets about 6,300 updates. At 50%, about 12,700. Neither condition reaches the threshold, so the model never starts learning. Transformer has no such threshold, so it degrades smoothly. Now let's just dig into why we got this result. Let's just start with the LSTM page transition. LSTM's gates have to coordinate with each other to build meaningful text representations. That coordination only starts after enough gradient updates have been accumulated, and that is why the model looks completely random until it suddenly isn't. This is not a bug. It is a structure property of how LSTM learns. Three results look unusual compared to what we expected from the literature. First, LSTM outperformed Transformer. In most published experiments, Transformer wins, but those experiments almost always involve pre-trained models. Without pre-training, one relatively simple dataset with clear vocabulary patterns, LSTM turned out to be fully competitive. Second, Transformer overfitted more severely. We used a lower dropout rate for Transformer, 0.1 versus LSTM's 0.3, and we did not apply any extra vocalization like label smoothing or learning rate decay. Third, Transformer's validation accuracy stayed flat, even as validation loss increased. This means it was not making more mistakes. It was getting more confident about the mistakes it was already making. The model's calibration got worse, but the error count stayed roughly the same. Beyond unexpected result, there are also three ways our implementation ended up different from the original design. First, the ablation hypothesis was reversed. We went in expecting Transformer to be more data sensitive and designed the study around that assumption. We had no thought about LSTM convergence threshold at that time. Second, we changed the padding strategy mid-project. We only originally planned to use padded sequence to fully exclude PID tokens from LSTM computation. We end up using padding index equals 0 instead, which treats PID as a 0 vector rather than skipping it entirely. The practical difference is small, but it was an unplanned change. Third, the checkpoint selection criteria end up being different for the two models. LSTM saves the checkpoint at the epoch with the lowest validation loss, and that turns out to be epoch 8. Transformer saves at the epoch with the highest validation F1, and that was epoch 10. If we had used the same criterion for both, we might have selected a different Transformer checkpoint. This is something we should have decided before training. Let's just look at three cases where the models made wrong predictions. First, a golf article sponsored by the Deutsche Bank was labeled business, but both models predict sports with high confidence. The content reads like a sports events report, so the model focused on the right signals. The label is what looks ambiguous here. Second, a Nintendo DS game review revealed SciTech was correctly predicted by LSTM, but Transformer predicted sports with 99.98% confidence. Action words in the review, like draw, trampoline, and jump, pulled the attention mechanism towards sports. This shows how Transformer can be overconfident when the surface level vocabulary is misleading. Third, a North Korea article labeled Word was predicted as sports by LSTM. The raw text contained HTML in titles like this. left over from web scraping. This broke word boundaries during tokenization and confused the sequential representation. Transformer was more robust to this kind of noise. To wrap up, LSTM had higher final accuracy, 92.76% versus 91.30%. But LSTM failed completely in the evaluation at 25% and 50% data, while Transformer held steady between 87% and 90%. So which model is better? Really depends on what matters to you. Here are 3 things we learned from this project. First, accuracy alone is not enough to judge a model. Transformers scored lower, but was more reliable when data was limited. Second, LSTM convergence is threshold-based, not gradual. Without understanding this, the ablation failure would look like a bug rather than a finding. Third, small inconsistencies in experimental design, such as using different checkpoint criteria for the 2 model, make fair comparison harder than expected. Thank you very much.